multivariate regression a little bit at the end so that you can start seeing it in the lab class. So we'll go through again the matrix formulae for that. The key things we also did was introduce matrices, linear algebra, and derivatives, multivariate derivatives, which are going to be important for fitting all these. All these things are important for these sort of so-called linear Gaussian models. Very important. Now, what we're going to do this time is we're going to introduce basis functions for nonlinear regression. Now, basis functions are a really nice trick because actually our model, in some sense, will retain linearity, but it's going to be a nonlinear model. And the trick is that we're going to build models that are nonlinear in the inputs, but linear in the parameters. So you'll hear people talk about these things as linear models. They don't mean that they're linear models in terms of the prediction function is linear. They mean they're linear models in terms that it's linear in the parameters, as we'll see. And the way you do that is you introduce basis functions which take your data and you push the data into a nonlinear space. And actually, what you do if you do it in 1D is you end up converting a one-dimensional regression into a multivariate regression. In some sense, we've already seen sort of basis functions because the most simple linear regression case, what we sort of said was that I meant to test pens today, but I forgot. We've got x, and instead of saying mx plus c, we said we'd have w1 times x plus w0 times 1, which is effectively augmenting our data set. That's sort of saying that each data point, we have not just an xi associated with the data point, but a 1. And that 1 is like a basis function. It's a function of x, which is not a function of x. It's constant. But more generally, we can use this idea to perform nonlinear regression. So the key idea is that we have a prediction function f of x, just like our prediction function before. Our parameters are still w, but instead of the parameters operating directly on x itself, we create these nonlinear functions. These are the basis functions which operate on x. So here it's shown for multivariate input x, but we'll actually focus on one-dimensional input x in class today. Sometimes this is called a feature space. So you'll hear in support vector machine literature, you'll hear this talked about as a feature space. This also is, if you've heard about neural networks, this is a neural network as well. If these are the neurons in the neural network. I don't really use that terminology because statistics and basis functions existed a long time before that. This is even what Laplace had to do and Gauss had to do. When Gauss was predicting where the orbit of Ceres was, he derived basis functions, but his basis functions were dependent on the laws of planetary motion. So they're sort of sinusoids with weird twists in them because of the fact that the Earth is spinning. So his basis functions were based on his understanding of physics, which is actually a really important idea. That was a mechanistic understanding of physics. Now, we often don't have a mechanistic understanding of our data, so we come up with more generic basis sets. But you can see here that what f of x is a weighted sum of some nonlinear functions. So, however, f of x is linear in W. And that's sort of a little bit clearer when we write it in inner product form. But it's just a sort of sum. The w's are not inside a nonlinearity. They're outside the nonlinearity. So this is a sort of global basis. So this is a classic basis, a quadratic basis. So polynomial curve fitting is a basis function model. I mean, splines are basis function models. Loads of things are basis function models. So the first basis function here is a very, very simple one. Phi of x is 1. It doesn't matter what x is, phi is 1. Now, what we've been working with so far is a sort of first order polynomial basis. We've been doing an m times this basis function plus a c times this basis function, which is mx plus c. So we've been adding, in effect, a constant times some weighting to a linear times some weighting. If we go quadratic, then we just add the next order. So the quadratic basis, so the 0 on this axis is here, so the quadratic basis function is this one here. Phi of x is x squared. So now we can actually add 3 of these together to form different functions. So it's nice and simple. If we want to sort of look at the type of functions we get, here I've just taken some, it's a basis function model where we've got f of x is a constant plus, this would be m, what we've done before, times c plus w3 times x squared. So actually, sorry, I've got a mismatch between my notation here. Let's just fix that for you. I'm going to fix that on every slide. But, so here, W0 is the constant, and it's multiplied by 1, and it's 0.98. So that's saying that the constant offset is sort of up here. So actually, if you look at where this is the blue is the sum of the 3 functions, right? The thick blue. The thin blue is the quadratic, and the magenta is the linear. Now the magenta is being multiplied by W1, which is 0.35. So it's saying it's slight positive slope, because that's what physically it means, the m parameter. And the W squared is actually giving us curvature. So it's not quite as simple in the first, if we do the derivative of this, actually the gradient changes, so the slope is varying, right? So it's not as simple as when it's y equals mx plus c, and m is clearly the slope. But actually, W2 is the curvature. If you take the second derivative, you'll find that the second derivative is W2. So it's got a slightly negative curvature. Yeah? So it's a rising function because W1 is slightly positive. It's offset from 0 because W0 is positive. And it's got slight positive curvature. Positive curvature, remember, a maxima would have positive, so negative curvature. Negative curvature, a maxima has negative curvature, and a minima has positive curvature. So this is slightly negative curvature. So that's a concave function. How do you remember the difference between concave and convex? Come on. Concave, cave, concave, cave, concave, concave, man. Wearing in a cave, concave, concave, concave. A man with a cave, concave. There you go. So here's another concave function. There's no man in this one. Again, W here, 0 here has been sample positive. So if you look at the 0 point here, it's 0.94. If x is 0 in this equation, the function will be 0.94. Strongly negative curvature, so we're seeing much more of the curvature here, and the slope is only very small and positive. So if you look, this should be symmetric if the slope was 0. If you look, this end is slightly higher than that end. There's a slight twist on the function. And this one again has now got a negative W0, but same idea. It happens to have a negative curvature. I sampled these randomly. If you rerun the notebook, if you go and run the notebook, you'll see other ones. They're all sampled randomly every time you run the notebook. Okay? So that's a sort of classical thing, polynomial fitting, and we'll do some fits of polynomials at the end of the lecture to the Olympic data after we sort of re-derive. Because believe it or not, you sort of have everything you need already to fit these models, because we did multivariate regression. Because although the input's one-dimensional here, in effect, we could see it as a new regression where we've got a new set of inputs that's three-dimensional. Yeah? So if I didn't tell you that these were 5s, that these were, if I was a client, I could either come in as a client and say, here's your x's, and just give you what I've pre-computed, x and 1 and x squared, give it to you and say, please do a multivariate linear regression on these x's. Or I could come in and say, here's just my x value, you choose your basis functions. So you can see how these basis functions sort of are equivalent to features. In fact, in neural networks, in all this thing everyone's crazy about called deep learning and everything, what they would argue is what's going on is automatic feature extraction. Now in neural networks, something more complex happens because you actually don't just optimize these linear parameters, you optimize parameters inside the basis functions. But we'll not We'll not go too much into detail because it's just so trivial to explain neural networks once you understand basis functions, and so we're not really going to have a specific section on them. Okay, here's another basis that is also interesting, and the reason I chose these two is that first one was global. So any change in the parameters has a global effect, typically. So if you change the offset parameter, you shift the entire function up and down. If you change that slope parameter, you twist the function all the way across the domain. If you change the quadratic parameter, I mean, actually with polynomials, as we'll see, they get really messy. Because as you go outside the range of -1 to 1, you start saying x to the power of 6. And if x is 10, that's 10 to the power of 6. And so if you change the coefficient in the thing that's 10 to the power of 6, you get a dramatic effect across your function. So it turns out that polynomial basis is a really bad idea. I mean, they're nice computationally for several reasons. But in terms of your modeling, they're a really bad idea. But they're fun because you're sort of familiar with them. You've probably looked at them before. So this sort of basis is something that is often used. I don't like the term Gaussian basis. You'll see it's called that. The reason it's called that is because it looks like a Gaussian form. It's e to the x minus some mean, some location parameter, we should say, squared divided by some scale parameter. But this isn't a Gaussian because it's not a density, right? So we're trying to use the term Gaussian to refer to densities. And I don't want you to get confused about the fact that this functional form is the same thing as the Gaussian density. So I'll tend to call it a radial basis, or I might call it an exponentiated quadratic, because it's a quadratic that's exponentiated. You'll also see in the literature sometimes it's called a squared exponential, which one of my friends really doesn't like because it's not a squared exponential. That would be something different. So I started calling it exponentiated quadratic. So what I've plotted here, I've actually put in parameters here, so I've multiplied this out. So if you're confused why that doesn't look the same as that, what I've actually got is a location parameter here as -1, and I think an L squared parameter of 2, a width of, an L squared parameter of half, I think. Yes, an L squared parameter of half on these bases. So I've got one basis function. Now this basis function has a parameter, its location, where it's centered. And what I might do, if I was using these sort of bases, is I would locate them at different places. The previous basis function also had a parameter. That was the degree of the polynomial. Yeah, so each basis function itself, phi, had a parameter which was either 0, 1, or 2. X to the 0 is constant, x to the 1 is 1, x squared is squared. So we can think of that degree of the polynomial as being a parameter. This actually has two parameters. It has one parameter that's basis function dependent, the center of where you're putting the basis, and one parameter that is global, how wide these functions should be. Now the nice thing with these sort of basis functions is I think you already start getting some quite cool looking stuff. So why we say they're local? Well, because they decay away to 0. They have sort of no effect outside some distance dependent on L away from their mean. So when you add one of these basis functions in, let's say we saw a new data point over here and we had a basis function associated with this data point. That basis function would sort of numerically have no effect on what's going on the far side. So that's why they're local. If we were to add a basis function in on the polynomial case, then it would have a potentially dramatic effect. So here's a sort of a sampled weighting of that. So in this case, we're just taking a negative of the center one, fairly large negative, minus close to square root of 2, square root of 2 over 2, sorry. And then I've got a small negative on this one as well, so you're getting a slight dip as we move down, and then a little positive here. Notice they're not summing up, in this case, to give us 3 separate bumps. We don't necessarily have 3 bumps because these curves are adding together to give us a nice smooth curve dropping down. Yeah? So when these sort of things sum together, you can get nice looking functions. Here's another sample where we've gone quite clearly negative, heavily positive, and then negative again. So it's like a Mexican hat type form. We're sort of going down and then up and then down again. And then finally another example. Let's see what's happened in this one. Oh, that's a bit annoying because it's the same as the last one. How boring. Okay, so that one's not so interesting. It's just similar to the last one, right? So the prediction function, okay, I should probably have dropped the plus c. Let me get rid of the plus c, because you can now think of c as a basis. If we want to have c in the model, we can just always think of adding a new basis, right? So we can always think of a basis function that itself is just phi is equal to 1. Phi of x is equal to 1. Yeah? And then a parameter associated with it. Now, but what I've written here is to highlight that these things can now look like features. So normally, when we have a multivariate data set, we always are doing things in terms of design matrix. So we've got some matrix X where it has n rows. That's the format of the design matrix. I think we often say Q columns. We could say P columns if it was output data. And then each element of this matrix is x1, 1 up to x1q, and then xn1 and xnq. Right, index on here. Now the point about these basis functions is you can compute the basis function. So now what we're doing is we're saying, actually, instead of what we had before where we've got just x, we're creating effectively a new x. So our x now may be just, in this case, it's just one-dimensional, x1 all the way down to xn. But we're creating a matrix, so this is matrix X. We're now creating a matrix phi, so that's a capital phi. Or I think the Greeks, anyone here Greek? I think in Greek you say phi, actually. But the problem is that if you did that, then you would say, you would pronounce pi as p. And if you pronounce pi as p, then no one would know when you were saying pi and when you were saying p. So we say phi. I think the right word is phi. So phi, capital phi. This is capital phi, this is little phi. So now we've got this phi 1, 1 down to phi, and let's say we've got m basis functions. So this is something we choose. M basis functions. With our input space, q is 1. It could be more. I mean, it still works if it's more. As long as they're multivariate functions, it still works if q is, you're sort of ambivalent to it then. Then you've got phi n1 and phi 1q. And all the ones in between, obviously. You don't just have 4. Just illustrating the size of the matrix. But here, you need a machine to compute these for you. Your machine is the function. Right? So, and that's what I'm trying to denote here, is that what you're going to do is you've got a function phi, you give it, your function is associated with one of these outputs. So here we've got 6 basis functions. So this is one of those 6. So it could be phi 1. So in order to get this element here, you compute phi 1 on x1. And that gives you that. To get this element here, you compute phi q on x1. That gives you that. Yeah? So the function is operating as a little machine to give you this new basis. But then once you've got that, it looks exactly like this. Only it's much more difficult because it's represented by a Greek letter instead of a Roman letter. It's not really more difficult. It's just the same. So this sort of notation here is designed to represent that. And this is our prediction function. So we need 2 things in the model, the way we've been describing the model. We need the prediction function and we need the objective function. The prediction function is what we're going to use for new data to say what we think is going on. And the objective function is how we're going to fit the parameters of that data to that model to the given the training data. So this form of notation is nice because this form of notation, now I apologize, there's a bug in the Jupyter notebook that came with the last version. I can't bold that phi. I tried this morning for about 10 minutes to bold it. So it should be bold. It's not actually. It should be bold because it's a vector. Because this phi here is the vector from the ith row. So it's phi I1 up to phi IQ. It's that vector there. And what we're saying is that the prediction is given by the inner product of W and phi. Now the really nice thing about that is, why I like that form, is you can see the model's linear very quickly. I mean, you can see it in the sum form too, but this is really obvious. If you can write your model in an inner product form, such the parameters are an inner product with in the prediction function. That prediction is linear in the parameters. It's not going to be linear in phi unless phi itself is a linear function. Yeah, so it's not linear prediction, it's non-linear prediction, but it's a model that's linear in the parameters. It's an important distinction. Oh, and we were getting rid of this, weren't we? So it's just the same as before. I mean, this is exactly what we did last time, but perhaps worth looking at again, just because you know, it's the first time you saw it was last week. We're now making a prediction for our y. If we're going to do Gaussian noise on the regression, what we say is that this function, the prediction function, is the mean of a Gaussian density. So this is the target value, and this model is saying that I expect y to be distributed as a Gaussian with a mean given by W transpose phi I, or f of xi, and a variance given by sigma squared, or a standard deviation given by sigma. So we sometimes write these models down as we say that the yi is f of xi plus epsilon, and epsilon is Gaussian with zero mean and sigma squared I. That formula is equivalent to saying this, because this is deterministic. So this is just saying that y is equal to a Gaussian with variance sigma squared plus this deterministic thing. So if you add something to a distribution, you just shift its location, you're just changing its mean. So that's why f of xi, which in this case is yi equals W transpose phi I. That's why the mean is now that. Any questions on that? So that's how we turn the prediction function into a likelihood. So actually, I'll just pause there for a moment for questions, because we're going to move into the derivation of the likelihood, which is very similar to the one we did in the lab class last week. But I'll just pause there quickly and see if people are clear on what we're doing so far. Yeah?
I have one question.
Yeah.
Specifically, I'm a little bit curious about this two-dimensional matrix that you have here. I'm just curious, I understand that for each computation of some xi, you're computing phi I, but how do you know which function is being chosen to be computed and put into that 2D matrix? I didn't understand that part.
Okay, yeah, that's good, because I went through that too quickly, so thank you for asking about that. Let's try and look at this example here. So this example here is, we've got these three functions. They look complicated, but all they are is just changing the mean of the Gaussian. So in order to create this matrix for this example, given x, so this, in this case, this m would be 3. Yeah? And this is going to be n. We don't have the data here. What we do for each data point, we take x1, put it into this, so I've had W0. Sorry, that was on my finger, not even the pen. So this function here is phi 1. Yeah?
I get it now.
And this function here is phi 2. And this function here is phi 3. So phi 1 comes from x. Phi 1 phi ij comes from phi j and xi. So unfortunately, I have to flip the index when I do that. Yeah, you did have it a moment ago, and now I've just confused you by sort of saying it that way around. So we've got phi 1 of x3, where phi 1 in this case is equal to e to the minus 2 x plus 1 squared. That's phi 1 of x. And that would give us phi 3, 1, just because the x is on the third row and the phi is on the first column. Yeah? You're going to do this in the lab class.
I think I get it.
Yeah?
Yeah.
So in some sense, the function is just a machine for generating this feature space. It can be thought of as sort of a mapping into a higher dimensional space as well. So that's why people talk about it as a feature space. And you'll hear people talking about that in machine learning. So the support vector machine, if you read a lot of material on the support vector machine, which we're not really cover the support vector machine algorithmically, but you can see it within these class of models. They're doing this clever trick where you actually you make this feature space infinite, which is something we'll touch on right in lecture 12, how you can make this feature space infinite. Because here you've got a choice of functions. But they'll always talk about that. They'll say, oh, we're going to project into an infinite dimensional feature space, and then we'll do a linear decision. It sounds super, super complicated. But actually, you already know 90% of the way there. There's just one final trick you need to make the space infinite, which is a mathematical trick. Okay. So under the assumption of independence, we can write down the log likelihood of this. So remember that this is our likelihood for one data point. So in order to get the likelihood for the entire data set, we have a product of these, if we're assuming independence and identical distribution. So we assume this is the same for every data point, but it's independent. And when we take the product of those and take the logarithm, we get that. It's the same as before, same as last week, only this time, instead of W transpose X, it's W transpose phi. Now, just as before, we by convention, when we look for the objective func it on. I quite like that. I think we should call it a func it on from now on. Objective function, it has this sum of squares form. So the objective function is the negative log likelihood. Why do we take the negative? Because it's convention. Just as it's convention to put data points down the axes, just as it's convention to have features on the columns, just as it's convention to drive on the left and not on the right, it's convention to minimize, not to maximize. Yeah, so that's just, we talked about that last time. In optimization, we talk about minimization. That just avoids confusion, because then you can talk about convex optimization, which we have as a convex function, the opposite of a concave. I don't know, that's not a vex. It would be good, it should be called concave, shouldn't it, or something like that, and then it would work. But no, it's not, it's called convex. If you remember concave, then you remember that convex is that way up. What's a stalactite, what's a stalagmite? Come on, which one's on the ceiling, stalactite or stalagmite? Stalactite, thank you, why? Because it's tight, it's having to hold tight onto the ceiling. Yeah, same thing. You don't need that for the course. That would be cool. I'm going to ask that on the exam now. Multiple choice question 1. Okay. Once you've got it in this form, the main work you've got to do, you're going to have to remember the multivariate calculus differentiation rules that you're sort of looking at last time going, oh my god. But actually the main work is just multiplying out the brackets. So you need to turn these into something that you can do the differentiation through. So you were distracted. You were distracted because you thought you knew how to multiply out brackets, and you didn't pay attention, and you forgot one aspect of how to do this. So we're going to prove that that's the case by asking you what each term is. So if I multiply out the brackets on this term here to get the quadratic form written out, so let's ignore the 2 sigma squared, we can bring that in later. Let's ignore the sum, we can bring that in later. Let's just look at this bracket here and tell me the first thing I should write down. So we're just going to take that bracket and multiply out the 2 of the brackets, yeah? So it's a quadratic form, multiplying out one bracket times the other.
I squared.
Oh, thank you, thank you. I squared. So that, you know, you can imagine, I mean, I always, in my head, this is what's going on, but I don't actually write this down anymore, right? In my head, that's what I've got. And I'm saying that times that is giving me that. So what's the next term I can write down? I hear, it's good because it's commutative and I hear all the terms correctly, so it doesn't matter. I heard a minus, so let's put, I heard a 2, I heard a minus, what else did I hear? yi W transpose phi I. Yeah? And then the last term. What do I write down for the last term? Pardon? Plus, yeah. W transpose phi I. Now what? Squared. Okay. You all did it wrong. I told you you weren't paying attention. I told you you weren't paying attention, and I was totally right. Do not write that down. If you write that down in the exam, you'll go, oh my God, how do I differentiate that? When you look at your rules of multivariate differentiation, you won't find a rule for that. I mean, there is a rule for that. The rule for that will be hidden. Always write this down. Yeah? W transpose phi I transpose W. Now you found the matrix. The matrix has appeared. It's not what it was in the Keanu Reeves film. That's how the matrix comes about. The outer product of two phis. Okay, so now let's worry about the things that we ignored before. So let's put them in. I should have left space. I mean, it's much less complicated, isn't it, if you put them in afterwards. 1 over 2 sigma squared, sum of 2 yi, I equals 1 to n, and then the sum of I equals 1 to n, 1 over 2 sigma squared. So that's the main part that we need, because this part here, if we're going to, I mean, if you do the differentiation with respect to sigma squared, you need this part as well. But when you're doing the differentiation with respect to w, that part doesn't depend on w, so it just disappears. So now we're going to do the differentiation, and I gave you the rules last time, so what's the gradient of that with respect to w? 0, great. Harder. What's the gradient of this one with respect to w? Let's have a look at the rules for differentiation. What's the gradient of this one with respect to w? How's w appearing? Which rule do we want? Do we want that one or that one? Hum louder if I'm on the right one, hum softer if I'm on the wrong one. That one or that one? First one, yeah. It's an inner product, so we want the linear term. And let's look specifically at the term itself. So look, this is all just confusing you. It's just hiding the true answer. What's the answer to this? If we just look at that part, what's the answer? Phi I? Yep. But that part's constant. So in front of the phi I is 1 over 2 sigma squared sum of 2 yi. I equals 1 to n. Now have a little sanity check. Always have a little sanity check. Is your dimensions right? I should probably just put a little line under that to indicate that phi is a vector. You can put a line on top. If it's going to be the gradient of the thing with respect to w, this has to be a vector. We expect the gradient with respect to w to be a vector because it's this multivariate gradient where we've got a scalar here, and then we're doing it with respect to each element of w. So we're going to get a vector. This is gradient of A1, of A transpose W with respect to W1, A transpose W with respect to W2, 3, 4, 5, 6, 7, 8, 9, 10. So you always expect that to be a vector. Is this a vector? Well, it's the sum of a bunch of vectors, so that's a vector, and it's multiplied by yi, which is a scalar. So it's a weighted sum of vectors with a front weighting as well. So it's fine, it's a vector. So proceed. Next term. Okay, so I mean it's kind of clear now which rule. Which rule is it going to be? No, it's the third one. Haha, got you. Because it's symmetric. Yeah, it's the second rule, but it's that's great. You're always trying to encourage the audience to answer questions. So the best thing to do is when someone gets something wrong, is just to go, "You got it wrong!" So I won't be doing that. So don't worry, I'm never going to do that. What we've got here is plus 1 over 2. I've sat in lectures where people do that. I think it's brilliant. Okay, all that. So no, let's not write that down first. So what do I get from here using that third rule? That term there. So this is phi, this is the matrix, right? So what do I write down at the bottom? Yeah, phi I transpose times what? And what are we missing? 2. So 2 actually cancels with that 2 there when we pull this in, but let's just pull it in for the moment and cancel afterwards. 1 over 2 sigma squared. So now the 2 cancels there, and we're done. We've got the gradient in an ugly form. Fortunately, in true Blue Peter fashion, here's one I prepared earlier. Now, we've got a sign wrong, have we? Ah, yeah. Look at that. We've got a sign wrong because I failed to update the slides. Let's just get that fixed, because what you saw there was the gradient of the error of the likelihood. So the sign was the wrong way around for the way we're doing it. And then let's get the signs right. So much more convenient being able to edit my mistakes real time. So the reason we had the sign wrong there was because we were showing the likelihood of the gradient with respect to likelihood. I've changed that to the gradient with respect to the error function. So what we're seeing is, yeah, this 2 cancelling with that 2, giving us phi I yi. 2 cancel that. Minus 1 over sigma squared phi I yi plus 1 over cancels 2 again, sigma squared phi I transpose. Now, I like to write that bracket around, that square bracket around, the sum, because that shows, I mean, we could also do the same thing here, actually, a square bracket around that, because what's in the square bracket is actually a matrix and a vector. It's a little bit confusing because you've got the nasty summy sign here, but the sum sign is hiding the fact that that's just a vector, and the sum over vectors is a vector, as we talked about before. This is a matrix because it's the outer product of 2 vectors, and then it's a sum of a bunch of those matrices, so it's just a matrix. So that is a matrix. Now, that can be solved in this way, but you must never solve it in this way, because solving it in this way turns out to be very numerically unstable. So what we've done here is we've sort of moved that term over to that side, cancel out the sigma squared. Look, we can divide this, multiply this whole thing by sigma squared. The sigma squared disappears. That's something really convenient, right? It doesn't matter what the noise is for the solution for this. That's unusual. It could matter, right? It doesn't matter the scale of the overall noise. It just disappears. So then when you get the solution here, what you're seeing is you've got this matrix inverted. Was that matrix reloaded, wasn't it? Matrix inverted. Was there a matrix inverted? No. That would have been a better film. And then times a vector. Okay? But don't solve it in that way. So don't solve it in that way. You'll find that for some cases it's very numerically unstable. So this is just saying, oh yeah, sorry, I've got my lessons out of order. Let me get that lesson done first. Although I've introduced a new notation. What you do in practice is you use this solver, which is actually for solving systems. So the way what you're supposed to do in linear algebra, if you've got a system of equations of the form, or what do they call it, ax equals b as their sort of standard linear algebraic notation. And if you want to solve for x, find the correct x to solve this, you can immediately write down, yes, that x is equal to a inverse b. But you mustn't solve it that way, because you can get severe numerical problems. I mean, you can write the math down because the math is exact. But when you write it down on a computer, what you do is it's called solving this system for x. And there's a routine that does that for you in NumPy. It's linalg solve. In fact, underneath the hood, the stuff we're not teaching, there's all sorts of different routines that make sure this is all numerically done. It was all worked out sort of in the 70s. There's entire journals filled with the right way of doing this. We don't have to worry about that level of abstraction. We're just going to ignore it, but sometimes it pops up. So for example, if this matrix is triangular, if it's positive definite, if it's all sorts of different forms, if it's sparse, you get different routines for solving it. Now this isn't even the right way to do a linear regression, and you'll see there's some additional notes at the end of last week's class explaining that you have to do it by QR decomposition. That's the most numerical, but I'm not examining you on that, I'm just pointing out that when it comes to solving these things, it can be a little bit involved. But I want you to know the maths first of all. Because the solving, you know, it does generalize to other systems, but it doesn't necessarily generalize to other machine learning models. The bit I'm trying to teach you is the bit that generalizes to other machine learning models. Now, this is cute. I like this because I prefer everything. I like getting rid of these things. I think they're quite ugly. Some people like them. I don't. So you'll find that I tend to try and get rid of them, and I use these rules to do it. So this is that old matrix phi, that big fat matrix. So let's bring it back in by denoting it phi. Now, if I take one of those matrices phi and multiply it by another of those matrices phi, what we see is we get this thing out. So let's do that. So let's have phi transpose, which is this. It's a sort of that transpose multiplied by phi. So this is phi, and this is phi transposed. We've got that the wrong way around, haven't we? Now, it's a little bit hard to see, but what multiplying these two together will lead to is an m by m matrix. Why is that? Because this matrix is now m by n times an n by m. And I went to great lengths in the previous thing showing you that those things sort of cancel, and then you get an n by m. Now when you do this multiplication, what you actually get is each of these steps is doing that sum all at once. Each element here, so this, and let's see, think of the top corner element. The way we get the top corner element is by phi 1, 1 times phi 1, 1. So that's phi 1, 1 squared. If I matrix multiply this, I take that vector and I multiply it, that sort of row vector, and multiply it by this column vector. And right at the top, I get a phi 1, 1 times a phi 1, 1. But then I add a phi 1, 2 times a phi 1, 2, plus a phi 1, 3 times a phi 1, 3, plus a phi 1, 4. So actually, that sum is embedded in the matrix multiplication. So hidden inside this vector, that vector times that, I'm doing that sum as I sort of, because the result of the thing that goes in this top corner is phi 1, 1 times phi 1, 1 plus phi, am I getting it the right way around? 1, 2 times phi 1, 2 plus phi 1, 3, so on and so forth.
Sorry, this one
2, 1. Oh, yeah. Yes, 2, 1. Sorry, yes, quite right. Thank you. Phi 2, 1 plus phi 3, 1.
1, 2, 1.
So no, 2, it's going down there, right?
2, 1.
2, 1, 2, 1, 3, 1, 3, 1.
And it should be 1, 2, and 2, 1, then 2.
Which one, son?
First is the 1, 2, then sequence 2, 1.
Was n time n plus
No, because it's this, it's the same vector.
yeah.
And no, because this is phi transposed.
Yeah.
Yeah? You would be right had we not transposed it. If it was phi phi, then you would be right. But it's phi transpose phi. Yeah? Which is what's giving us that effect. So when you've got this, you're getting a phi 1, 1 squared plus phi 2, 1 squared, which is actually what this is. That's just summing the top element of that vector multiple times. I mean, the output of this outer product is to give us a phi 1, 1 here, but then if I is 1, but then when I is 2, there's a phi 2, 1 squared plus a phi 3, 1 squared. So it's a little bit hard to see. So I mean, these operations are sort of, if you remember Legendre's stuff that I put in the slides last time. I didn't put it in just for the benefit of historical context. I like the historical context. But look what he had to do. He had to write all those sums out. And magical of magical, when you do the matrix multiplications, those sums all just disappear. They're embedded inside the matrix things. As long as you then know all the rules for matrix calculus, you can then apply nice simple things on top without writing all these sums out. So it's a really important notational convenience for getting stuff working. How long have we got left? Similarly, for probably the easier one to start with is this one, phi transpose times y. Remember we said it was a weighted sum of y, so it's phi transpose times y. So this is n-dimensional. Sorry, it should be long, shouldn't it? Not short like that. So it's now each row of phi times y. So each element that comes out. So if we do this first row, what we get is yi times phi colon comma 1, which is the whole first column of phi, which is transposed here, so it's in the row form. So we get a weighted sum of yi times 1 of phi's, but then we get a yi, when we do the next one, we get the, we get the vector y times the phi's. Then when we do the next one, we get the same thing again and again and again, and in the end, the sum's just going in a different way, but we end up with the same thing. So we end up with a y transpose phi, where each vector of phi, remember when we looked at the gradient before, in here, it's a sum over yi's weighting the phi i's. But this form here, each phi is turned on its side, and then it's multiplied by its relevant yi, and then it's summed again. Sum being in the transpose, right, being in the matrix multiplication. So you can sort of get rid of these sums. These two little rules, they take a little bit of thinking about, but once you've thought about them, I would remember them. There's some real important notational conveniences for it to work, right? Number one, we never write down a row vector. Yeah? Never ever write down a row vector. You will see early work. There's a book I was reading where they actually write down row vectors. Fine, it's, you know, you could have done it in the past, but again, convention. Every vector is a column vector. So this actually is a column vector formed by taking a row of phi. So that's slightly confusing, isn't it? But it's a column vector that is extracted from the row. So that's why that maps to that, with the transpose moving. So the outer product of these things always moves to the transpose on the inside, because that column vector in here is embedded as a row. Once you've got that and you know you're confident with how you've defined everything, then these things are easy to sort of remember. So under the derivation we were doing earlier, then that means we can just solve in these terms. You can also write this down mathematically. You can compute this matrix in one shot. You don't have to do any weird sums over anything else. You just have to compute the basis function matrix, and then you can do the matrix multiplication to do that. In fact, what you'll see at the bottom is that's not the right way of doing linear regression. Because of numerical problems, you're supposed to do this QR decomposition. Okay, I'll just push through. I would take questions there, but I just want to show you, before I take questions, how this affects in practice. So this is, we're going to do some polynomial fits to the Olympic data. What I'm going to show you is the least squares error on this plot here, and I'm showing you the fit. So this is a zeroth order polynomial fit. So there's one basis function, and it's just a constant function. So all it actually fits to is the mean. It just finds the mean of the data. And the next thing we'll show you is the linear fit. So this is using a constant plus a linear. And look at the reduction in error, right? So massive reduction in error already. Quadratic. So this is now adding a quadratic basis function in. So it has this, it's sort of starting to recognize there's some slowing up. There's a data point up there, by the way, which is just off the plot. Yeah? As we increase the order of the polynomial, we get more and more complex curves, and we get a lower least squares. So see the least squares dropping down. I'm getting a more and more complex curve. So this is the problem now, that what we've actually done, which of these curves is right? So who thinks which curve is right? How about that one? Who thinks we'll be running negative speed marathons by the year 2020? Well, that's one of the things we'll look at next, is how we're going to do the how we do model selection. Because we've just introduced all this work, all this maths has actually introduced a massively powerful fit. The ability to do very, very non-linear fits to these functions. So this raises all the questions about how you select that fit. we'll look at that next time. What you're going to do in the lab class today is play with basis function models, do some weighted basis functions, combining of stuff together. I think then the next lab class. Now, for next week, I was going to make next week a reading week, but now it turns out I have to be away on the 10th of November. So we may do a lecture next week, so please pay attention to announcements. I haven't sort of finally decided because I was supposed to be away next week. I'm trying to juggle a few things. We may do a lecture next week. If we do one next week, or if we do one afterwards, then it will start looking at generalization. How we make a selection of what the correct model order is. So the point in the way we're doing things is you're supposed to be digesting what we say in the lab class. You can ask people questions about it there and putting these things into practice. But I've emphasized in particular a mathematical derivation because I have to set you an exam. So what things are easy to set on exams? Coding or mathematical derivations? Well, you can look at the last exams and find out, right? Okay, so there's some reading at the end, and time for just one quick question or a clarification point. I had to rush a little bit at the end. Anything? All clear? You'll all be able to do. You can ask. Do everyone get their feedback from the first lab? I hope to send second lab feedback today. You can ask things you want clarifying. I wouldn't spend too long trying to clarify the first lab. If you look at it, it wasn't that interesting, was it? Really, the marks should have been quite high. It was really just get you warmed up into the system. I'll try and get the second lab. I haven't checked that everyone's finished their marking. My plan is to try and get the second lab feedback out to you during the break. So if you want to have a quick look at that during the lab class and you want to ask some clarification, you can do that. Okay? Right. See you in about an hour and 10 minutes then.